My name's Tom Ormerod, and this is some work that tries to address the problem of where ideas come from when you're trying to solve a problem and you're stuck. And I haven't got the blip up. See, I can't do the task, can I? So what I'm going to do is talk about the current state of, what I think the current state of research on insight problem solving is, then introduce you a model we call Prodigy, which we kind of wish we hadn't because Jamie Carbonell called his model Prodigy with a Y, but it's different, which is implemented as an ACT-R model of solving the 9-dot problem and more recently Mendelev's cards problem. We are going to report an experiment which looks at how the tests predictions from the model on how problem difficulty can be predicted across 9-dot variants, and then look at transfer across insight problem solving episodes. And then I'm going to stop. I like this cartoon because it actually sums up what I think is one of the real problems with insight problem solving. He's saying to the cat, never ever think outside the box. And in a way this is kind of, I think, a truism, because actually if you tell people in problem solving, think outside the box, there's an awful lot of universe outside the box. Where do they look? So this is my kind of characterization of where I think we are at the moment in insight problem solving research. There are two kinds of schools of thought. One school of thought is the school of thought that it's knowledge that's the issue. That it's your prior knowledge imposes constraints on the moves you're prepared to sample. And you have to somehow relax those constraints in order to discover new knowledge, explore to find new things. And that's illustrated by Günter Noblick, Stellan Olsson and their colleagues in their representational change theory. The alternative theory comes from myself and my colleagues Jim McGregor and Ed Chronicle, which we used to call Criterion of Satisfactory Progress, but we've changed its name to Prodigy. And the idea there is that what people do is they try and select moves that appear to maximize progress towards a hypothesized solution. And the reason insight problems are hard is that the solution path does not lie on the one that maximizes progress early on. So it's a strategic account as opposed to a knowledge account. My own view now is that both theories are both right and wrong. And we've illustrated this in a paper we put in the Cognitive Science Conference a couple of years ago, using the matchstick algebra problems that Günter and his colleagues had devised. So the one on the left, my left anyway, is it currently says 2 equals 2 minus 3, which is wrong, and you have to solve the problem by moving a single matchstick. And this is predicted to be a very hard problem under the representational change theory because it requires you to come up with a tautology, 2 equals 2 equals 2, which is constrained by your prior knowledge that most mass functions have one side and another side. On the other problem, it should be easier. This is 100 equals 50 equals 50, where we present the tautology, and it should be easier because it kind of breaks the constraint that's there. And indeed, in our results, that's what happened. The tautology was harder to solve than the non-tautology. But if you change the values and you put in really big numbers, so 2 equals 51 minus 2, and you have to form the tautology, our theory predicts that that then becomes easier because you're signaling where in the search space you need to look for a solution. Whereas this one, 2 equals 1 equals 1, isn't so clear as to where you look. There's a lot of homogeneity, if you like. And indeed, that's what comes out in the results there. The difficult one becomes easy when you tell people where to look. Perhaps not so surprisingly. So both theories are right, but I think they're both wrong as well, in that neither really solve the problem of where people want to go next. They explain difficulty quite well, but they don't explain what you should do when you find you're stuck, when you reach impasse. And I think what we're trying to do is tackle the frame problem, essentially, how the mind determines from potentially infinite effects of information those that are relevant and irrelevant. Or as Newell and Simon put it in a quote in their book, the problem of difficulty lies in answering the ill-defined question, what can I do that I haven't tried? The question is likely to be answered successfully only if the problem solver has an appropriate set of generated selective heuristics for obtaining a few possibilities in a larger space. And they italicize the few there. So that's really the state we're at. We're trying to solve the frame problem. One way of solving it is used, for example, by Haley and Son, who have an explicit-implicit model, a computational model. And it's kind of neat because it has these strategic and knowledge-based components to it. They use things like riddles. A man walks into a bar and asks for a glass of water. The bartender points to a shotgun at the man. The man says, "Thank you very much," and walks out. You have to explain why. I'll leave it to you to work it out. What they do is that they solve their frame problem by recording all the solution attempts that humans make, including the correct ones, giving that to the model, and the model basically has to sort out which is the correct one. So essentially, they're feeding a finite set of information in which the model has to discover the solution, which is one way of solving the frame problem. Similarly, Ollinger, Jones, and Knoblich have produced a non-implemented model of solving the 9-dot problem, and in which they essentially say it starts off with a Gestalt idea that you impose prior knowledge that you can't go outside a square, and then you get over this by applying heuristics, which are illustrated in the dots on the right. Heuristics like lines can go this way, or lines can turn on this dot, or there are spaces outside the problem that are useful. And it would work, but without wishing to sound facetious, it's always easier to solve a problem if somebody gives you the solution first. And it feels to me that what's happening here is at very least people have been given very strong, finite sets of data in which to search for the solution. So what we've tried to do with Prodigy is to make it find a solution for itself. A related question, and one that's often ignored in insight problem solving, is what's the product of gaining insight? What do you gain insight for? And our interest is in what you learn so that you can do something in the future. Which is where analogical transfer comes in. And we know from Jick and Holyoake's seminal work that analogical transfer is a very powerful strategy for problem solving. But in their own work, they show that you only get really high rates of transfer between analogs of the radiation problem if you either give people an explicit hint to transfer, or if you make the conditions of problem solving basically that you could do nothing other than do that. If you don't give them a hint, rates are much lower. And indeed, some people like Saller and Gobe have concluded that this far transfer between problems that are superficially dissimilar but conceptually similar is fundamentally impossible. We had a paper in cognitive psychology. Incidentally, top tip for aspiring researchers, if you do work on insight, always put insight in the title. This has never been cited. Made that mistake. So what we showed in this, we took the ball problem, and the problem is you've got either 7 balls or 9 balls, depending on the variant, and you can use a balance scale twice to find one ball that is fractionally heavier than the other ones. What people tend to do is they tend to maximize the number of balls they weigh, so they weigh 4 against 4. Curiously, a lot of people weigh 4 against 5. This fails. By maximizing the 7-ball version, it lies on the solution path. The 9-ball version doesn't, because you have to weigh 3 against 3. We added an extra constraint in, which is it costs £1, we did this in Britain, to weigh each ball, and you've either got 8 pounds or 12 pounds. And if you get 12 pounds, that's fine, you can carry on maximizing without knowing why it's going wrong. If you get 8 pounds, you run out of money. And what we showed is that this sets up the conditions for far spontaneous transfer. So when people experience the 9-ball as a source problem and the 8-pound constraint, they transferred not only to superficially similar analogs like the 8-ball, but to conceptually similar but superficially dissimilar analogs like the rogue sheepdog problem we made up, the exploding nuclear plant one that we had, and even to a non-analog, the cheap necklace, because essentially you're transferring strategic knowledge of where to look. So back to the 9-dot problem. In earlier work, myself and Jim McGregor showed that if you give people the relevant knowledge of going outside the square, it's not as useful as if you give people the experience of failure. So giving people the first line as a hint, you'd expect, most theories predict, that the line that goes outside the horizontal line will lead to higher solution rates than an internal line. But in fact, the opposite is true. You get higher solution rates with the internal line. And the reason is that if you look at typical first moves, the first moves that people try with the horizontal line seem to make enough progress. They seem to be worth persevering with. Whereas the other version, you don't cancel enough to make sufficient progress, hence the criterion for satisfactory progress, name of the theory. So we've been developing Prodigy as an actor implementation of how people succeed and fail to succeed with this problem with Jim, Adrian Banks and Patrice Frisconi. And it has two components now. It has this progress monitoring component, which is how to measure your progress as you go through. But it also has this new component we call idea discovery. And our ideas, our solution to the frame problem, is that Prodigy relies entirely on its previous attempts. It looks at what it's already tried and tries to understand them. If you look, for example, at these two attempts, that's handy, but timing's gone. These are two look-ahead attempts, that is, you're planning 2 lines in advance. And they have the same outcome, basically, they're both wrong, but they have different properties. They have different line lengths available within them. They have different angles available with them. They have different trajectories. And Prodigy basically parses its previous attempts to find properties that may allow it to discover new rules by simply swapping moves around or recombining them. And we've implemented that and found that it produces an ordinal level of success in predicting human performance. So the 9-dot problem it's solving at 0.2% of the time, compared with 5% in human data. So it's underperforming, but it's trying hard. It's doing a 10-dot version at 2.8% of the time, and the 11, 12, and 13 is solving all the time. So it does simulate in an ordinal way. The experiment I'm going to talk about in the last remaining 4 minutes looks at a test of that. We took the standard 9-dot and compared it against a version where we spaced the dots a bit, because we predict that this should provide a perturbation in the array that people can use to discover that line length variation quicker. They have the same solution. We also compared it against a different version of the standard problem where you only have 3 lines to solve it. And the theory predicts that the 3-line version should actually be easier than the 4-line one to solve, because you experience failure much earlier in it. Basically, once you've drawn a line across 3, you're stuck. You have to look for something else. And we did the same thing with the spaced version. We had lots of participants. We gave them, we put them in either the 3-line or 4-line groups and then subdivided into regular or spaced variants for their source problem. And then we gave them a source problem followed by a transfer problem. So if you've got the 3-line source, either spaced or regular, you've got the regular 4-line as your transfer problem, and vice versa. They were presented with the source task, then they had a 30-minute filler lecture from me, and then they had the transfer task. And they drew their attempts on paper, which each time they said they got an answer, it was checked for correctness. They were given 10 minutes to find a solution, and we gave them a piece of paper with 10 slots on it so they could have multiple attempts. What we found was a really messy table, so I'll try and step you through it, was that, as predicted, the 3-line version as a source problem was easier than the 4-line version. We got more solutions to the 3-line version. The same effect was found in the spaced version, except that solution rates for both problems were higher. So that spacing is adding information that people are being able to access. In the transfer, we found that there was a strong transfer effect from solving the 3-line source problem to solutions in the 4-line transfer. You benefited if you'd had the 3-line first to solve the 4-line, but not the other way around. If you had the 4-line, it didn't benefit you solving the 3-line. So we think that Prodigy has a small part to play in solving the frame problem, and that small part is by it generating new moves based on applying the properties of previous attempts. So it's looking at the smallest space it can possibly find, which is what it's already done. It fits ordinarily with human data, and it confirmed our predictions that problem difficulty is determined partly by the experience of failure, fail early is good, and also by the availability of perturbations in the initial array that generate potential properties for new moves. And that the likelihood of transfer, spontaneous transfer, unhinted transfer, is determined by the experience of idea discovery in the problem source, and not just transferring knowledge of the solution. Thank you.